So now let's apply this to a chemical reaction. And let's look at hydrogen and oxygen. And we're going to demonstrate this chemical reaction by actually igniting hydrogen in a balloon and allowing it to explode. And when we do that, we're going to see quantitatively how much energy is actually released in the reaction of hydrogen and oxygen. But we also notice something very interesting. We could release hydrogen into the room that's filled with oxygen and nothing would happen. In fact, we could put hydrogen and pure oxygen into the same balloon and nothing would happen. And there's a reason for that, and that is that there's a barrier to that reaction. It's called the reaction barrier, and that reaction barrier is actually very significant. It's 430 kilojoules per mole, and that's in fact a barrier higher than the energy release when the combination of hydrogen and oxygen explode. So the first thing we have to do is to say, well, we know that pure oxygen in the same balloon won't explode. Let's calculate the energy that's intrinsic to the hydrogen and oxygen and compare that with the barrier height. So let's do that. Let's calculate the kinetic energy of oxygen. That's going to be equal to 1/2 times the mass of an oxygen molecule times the velocity of the oxygen molecule squared, and we'll just assume it's at room temperature because that's typically how we run these experiments. So if I look at oxygen, the mass of oxygen is going to be equal to the number of atomic mass units. That's 32 atomic mass units, and each atomic mass unit is 1.6 times 10 to the minus 27 kilograms. All right, when I calculate that out, that gives me 5.3 times 10 to the minus 26 kilograms for the mass of that oxygen. But now I have to put in the velocity. The velocity is actually quite interesting. The velocity of oxygen at room temperature, the average velocity is about 4.8 times 10 to the 4 centimeters per second. And the way I remember this is it's all fours. It's essentially 4 times 10 to the 4 centimeters per second. And it's very important to keep these orders of magnitude in mind, and we're going to continue to stress how important knowing those orders of magnitude are. Well, this means that it's 4.8 times 10 to the 2 meters per second. And so if I calculate the square of that velocity and I then place that into my expression for 1/2 mv squared, where it's oxygen in both cases, that turns out to be 6.1 times 10 to the minus 21 joules. That's a very important number. That's the kinetic energy of molecules in the room around us. Nitrogen has a slightly different mass, but it's very close, and so the kinetic energy of all the molecules in the room basically comes down to 6 times 10 to the minus 21 joules. And notice again we're using joule as the unit, and we know why. And in fact, in all of molecular science, the joule is the unit of energy. So let's come back then and compare that with the height of the barrier. Well, it turns out that the barrier height is on the order of 10 to the minus 19 joules. That is, the barrier height in these chemical reactions is much, much higher than the kinetic energy intrinsic to the colliding molecules. And that's why we can put all sorts of species together and they don't react until we introduce a way of increasing the kinetic energy so they can surmount the barrier.